Hello, this is the second part of this feature detection and the matching coverage based on the PowerPoint file that is 4C. So already I covered the part 1 that is up to the point of talking about eigenvalues and eigenvectors. Then the larger part of the coverage is something for today. So I decided to split this one to the first part being more or less of a repeat of last Thursday's class, and this is something new for the next Thursday's class. So let's see how it goes. So today main the coverage or main focus will be eigenphase and other application. In other words, that application is the key issues in this feature detection and matching. So let me just give some synopsis or the summary of what we covered in part 1 of the same PowerPoint. That's roughly first 36 slides, and this specific slide has 99 pages, so this is much bigger chunk. Anyway, last time we said that I have to capture the image, go through the cleaning and necessary transformation, then first step of, so actually so the next stage of computer vision is that finding the feature. The feature is that the more of interesting points or significant or worthwhile points of the image. So sorry about the saying points. The points means that the components. So it can be an edge, or it can be the point, or it can be a region or whole area. So it is necessary that in a given picture that there are so many details, but we are focusing on something very interesting or useful or significant in understanding the picture, so that items of significance or importance is known as features, and that features can be beginning with a point, or it can be the edge or the borderline. Sometimes we are lucky, then straight line, and the whole area of a region. So that is a very important step for identification of the parts and eventually understanding the picture completely. Then in doing so, that the feature or individual interesting points may be the identified, but maybe different the sizes or different direction, rotation. So maybe it is necessary that we got some kind of standard form, like a tree is the one form that is a standard form. So it can be enlarged or shrunk, or turned around or shifted around. So that kind of the standard unit is needed. In doing so, the mathematical the tool that originally invented by Leonard Euler in the 17th century is very useful in that we have a whole data about this information is a matrix of two-dimensional, so maybe 1,000 by 1,000 or 500 by 500, but we reduce it into single vector, so V1, V2, V3, like that on single vector. So instead of that 1,000,000 components, we have only 1,000. That's a big saving. Then eventually single value, that's eigenvector and eigenvalue. So we started talking about the verification, and we'll do derivation of those eigenvalue and eigenvector today. But anyway, this is a very useful tool for the the computer vision. So first one, it simplifies the data. Instead of a large, huge data, it gives just one vector or one value. Then the thing is that this one may lose some detail of original picture, but what we are interested in is the uniqueness of this vector that representing this whole data. In other words, that however complex it may be, this one will be uniquely determined and never being, unless there's some data change it, this one wouldn't be changed. So that invariant is achieved through those eigenvector and then single value eigen value. So we said that that magic formula is that A, that's a big matrix of real data, times vector that we have driven is the vector times lambda of a single value, but lambda usually those scalar comes on the front. So we have A times V, or big matrix times eigenvector is the same as eigenvalue times eigenvector. This vector, of course, is the same. So by finding out those vectors, and especially in complex data, there's a principal component analysis that the researchers has the well-established methodology of uniquely identifying individual member of a feature or person or object, and without losing its identity. So the first step, or the first biggest example of this the identity, or this the usage of eigenvalue, eigenvector, is eigenface. So face recognition become very important subjects, and nowadays that the identifying the people from like airport, and by just scanning through those cloud and finding the right person we are looking for is not that hard, and thanks to this technology of eigenface. So we'll start talking about that eigenface and the other application. Okay. Important application of eigenvalue and eigenvector is actually this eigenface. So I told you that eigenvalue or eigenvector is a way of reducing the data. So a data looks like the n by n matrix, but we can multiply this one with another vector, whatever that, 1, v1, v2, like that. That's the same as a value, single value, lambda, and plus then times the same vector we had here, v1, v2. So we can reduce a huge data into one vector. So the face itself has a lot of characteristics. This lips, noses, and eyes. So from the starting point, usually typically somewhere around in here or somewhere around in here, then it searches through, and the geometric data got collected, and they are recorded as n by n matrix. Then that one, with the inverse of a matrix, can generate that a vector, that's eigenvector, and eigenvalue. So one more time, that the concept is that the A is the matrix of original data times some kind of the vector that is derived and unique is same as a lambda and V. So this way that V can be used as instead of big matrix, we have just a single vector being used for representation of the face data. So actually this technique has been well developed. This lady's face is in a way trimmed up to just important part of the face. or rather it is in the feature part. The hair or other clothes is not the important because they can be changed anytime. So just the centerpiece of those face itself will be isolated, and from the main points of eye part, the nose part, and mouth part, and the general configuration, and then can generate a data down there. So with this kind of operation, that we can reduce the face data of one person into a vector. Then that can be represented or displayed into like a ghost-like silhouette, because it doesn't have no detail about those the nose color or chin shape, anything like that. But it has a unique the characteristic, the vector that represent that specific faces. So when you look at this, then we have the whole bunch of the face data, and those things are that's k squared by the times n. So k squared matrix now become those individual vectors. So what it is that we got say suppose there are 50 people. Some of them have same face maybe, but it's all different people. So there are like 64 faces in here. Then that creates a 64 the vectors instead of 64 like n by n matrix, or the k, there's a k by k matrix. It'll generate k by 1 by k the vector. So that makes the data much simpler. So that's the good thing about this the eigenface and used for the identification of the face. So the technique used for this kind of a reduction of a large database for face feature into vector, eigenvector, and eigenvalue is the PCA. You may remember there's some slide back that principal component analysis. So let's see what it is like. So there are some faces of very famous people. Some of you, the people you may know, some you may not, but usually they are world-known people like Bill Gates or Arnold Schwarzenegger, then Gwen Paltrow. Actually, I don't know this lady. Then Angelina Jolie, famous the actress. I'm sorry. Then Queen Elizabeth, so on. These famous people, their faces are very easily available. Use that face picture and make a data matrix of the face feature, and derive those eigenvector and eigenvalue, and we got the eigenfaces. So that is a vector. Then how do we calculate that eigenvector for the face? So eigenface data. That is done. So actually, the previous one is the eigenfaces, the changes to eigenfaces, and displayed like that. And then they can be used as an identification. So when you are looking at those, then there are quite a few people in the cloud, and then based on, so when camera catches this cloud, many people, then they will identify the face, isolate the face. And from that face feature, the eyes, nose, and mouth, then it'll generate the matrix of those feature data and calculate the eigenvector and compare that eigenvector from the database. So we do every those calculation for every identifiable faces. If the faces are hidden like that, or the somewhere half hidden like that, then it may not be possible. But as long as it can be identifiable, it is being done. Of course, that this picture doesn't process everything. So here's one clear-cut faces, but not the isolated or not processed. So anyway, so you can isolate that, and you can identify that these two people are important person, very important person, VIP, and that there's one person that's a blacklist, the bad guy that we try to catch. just maybe a joke. You can identify that one by eigenfaces. So it is all based on the statistical method known as principal component analysis. So here's some steps, but as they are running out of time, so I'll just go quickly. And this is actually from the statistics. Actually, it's one of those multivariate statistics. So you may heard about the factor analysis, multiple analysis of variance, MANOVA it is called, or the principal component, and the canonical, the cluster analysis. Those kind of techniques are used. They are being part of this multivariate statistics. So the way you go is that the objective method of determining underlying pattern of the data. So data in two-dimensional, they can be plotted, individual cell of the two-dimensional matrix, that's what we're talking about, A, can be plotted as dots. And then we want to know general trend. Where do they go? So the determining underlying pattern in the data and the varying areas of meteorological, like the climate, the application can be used. So when they are doing forecasting the climate, that can be used. Very simple matter to determine underlying structure easily. So that one I'm gonna show the how they look like. That actually is a matter of the inverting big matrix. So identify underlying dimension or principal component of a distribution. So we got a fairly complicated pattern of the dots. This is not just the two-dimensional dots, but it can be multi-dimensional dots. So multivariate analysis can be used for multiple dimension, higher dimension than 3 dimension. So anyway, what it does is that it is just seeing that which one is most the biggest chunk of explanation or the cluster we can isolate from the data. So it goes a first principal component and second principal component and the third, fourth, fifth, like that one. So if it is a K by K or N by N matrix, we have up to N different principal components, but usually the contribution of the later the addition are very little. So usually the first 3 or 4 component is more than enough to uniquely identify those data set. So phase data is a data set, and we can find the general tendency or general pattern. So the principal component is more like this. So here's a primary components that in the book, that this is the longest line. So this line is a principal component in terms of trend. What does that mean? Let me explain a little later. And then here's a ballpoint pen. So this one is main axis, and this is this blob is another main axis going like that in red. Banana, this is a little bit curvy, but we can generate a line that goes more like this. So that can be the more inclusive. Rugby balls looks here main the principal component, and the frying pan like that. And the CD can be any kind of the direction it will be. So that's principal component. So think about this line as a kind of typically suppose that this is a village and these are the houses. Like in Mongolia, that there are girls, one girl, another girl, scattered around, and this one can be quite a spread. Suppose that the city or the township wants to run a bus line. Bus line should have a fixed route. So the line should be, so what we are interested in is how can we draw a line or create a bus line where the distance from everybody in other words, that distance from this one, all summed together overall is the smallest. What does that mean is this way. For example, suppose that I decided to have the banana. This is principal component. Then for the people around in here, it may be great, but for the people around here, it's too far. So overall, total picture-wise, that overall distance is much bigger. So you are trying to find the nearest and shortest distance. That is what we are doing. So this is principal component. Then second principal component, for example, in here will be somewhere around in here, the biggest one. So somewhere around in here. It can be here and here, but this is the thickest, so it can be used for second principal component. This one may be here, the kind of fattest or the longest part, and then this one can be anyone like that. One thing for sure is that the second component or this axis must be perpendicular to the original one. So it should look like that. And this one may be somewhere around in here. And this blue-wise, it can be like that, or it can be like that. So there are X number of the choices, and then you have a principal component, and the second principal, third principal components, you can identify. That is the concept of a principal component analysis. So trying to find just a few, not like for 100 by 100, there may be 100 different axes, but just the 2 or 3 small numbers that can account majority of the whole data patterns. So that's the idea about that. Here's different islands or the rocks around, or the cat faces. So what's the nearest one? So so-called in statistics, what is called the least square method. That is that square from here to this line, perpendicular line, and you do for every member of the group, and make it as a kind of the smallest possible number. So in a way, even if this has a little scatter, but we are just combining that one into one chunk of the line, linear the equation. If we got this 2 group of clusters, then we still want to do, if possible, then we have a 2 group, but there's a 1 line that can cover or contain everybody with some error. So whatever the differences from the main line to actual object is a deviation or is an error. That's all statistics terms. So if you have the principal components like that, the data like that, so it looks like some kind of dots and stars in the sky. Then we say that this is a primary or principal component, and this is a second principal component. And this one is again that is the first principal component and the second principal component. If there's a 3-dimensional thing, then there will be third principal component, and the 4th, 5th, 6th is maybe possible, but we cannot draw that in a diagram except the maximum 3 dimension. Then also the purpose of that is that we hope data can be represented as just 1, 2, 3, only that small number of principal components, and that can account to say 90% of the whole data, then that's good enough. So same thing, though we can have the big data, like a 2-dimensional here, but 1 line, that's 1 vector, that's eigenvector that will represent this whole data cluster or the distribution. So the finding PCA principal component isn't that easy. So we have a feature data set, so we got all those dots, and we got certain patterns. So we have one group like that and another group like that. This is different diagnostics of actual data. In here, we kind of see that this is a clear trend. So this is principal component. In here, it is a little difficult. So somewhere around there, but it's weak. So we will need one more like that, two principal components, and hopefully that covers like 80% or the 85% of total the characteristics of scatters. So that's what we are using it for, the principal components. So principal component analysis is used in many application, but one very good application is in finding eigenphase that the PCA is used. And this of course you can have that based on those certain points here, but despite those differences that we have this is a principal line, then each time there will be some errors, deviations like that one. So for the given value, each of dots, this one has a certain the deviation, what the errors. This one has some errors, but those things are all gathered together as a kind of the total scoring. And then this is second, the principal component. So remember that each principal components or every principal components are perpendicular to each other. So only in 3D, up to only 3D, a human can identify the perpendicular thing. In 2D, then this is perpendicular, this is perpendicular. 1D, only one thing, the perpendicular. Then in 3D, then this can be perpendicular. So there are as number of dimension increases, the number of perpendicular line can be increasing to that dimensionality. So that based on that, then it calculates the eigenvalues, and then the eigenvalues and eigenvectors all added up, and then we have the one vector that going through those principal, all data set. So this line is principal component. So we may want to go to a little higher on here. So this one tries different location. But anyway, there is the one principal component that as a vector, the line. So you see that the two scattered, this scattered line that goes to two-dimensional matrix. But we have an eigenvector, either this one or that one being used. So that is one-dimensional, the vector. Then those amount of spread is called the magnitude. So that is our eigenvalue, lambda1 and the lambda2, the amount of coefficients. So that's how we go that some data exists, and then we have the two-dimensional data like that. They can be used into matrix form and gets into u times the I squared. Remember those, this one is variances and this is covariance, their relationship. So with those the data arrangement, you can generate this the amount of the evaluation. So when we are looking at that, when you are doing feature detection, remember that we have been talking about the feature in this portion, that the feature, detection isn't really like based on those eigenvectors. So instead of going all those dots, we are going as just one representation of vectors for every data set. So we got those the values, and there are some differences in here. So feature detection can be done by finding this x value and one lambda and another lambda and x plus relevant feature detection. So sometimes depending on the amount of error we can see whether this one is the correct estimate or it is not. So anyway, the where it is changing fastest, that is showing as eigenvalues in ellipse shape. Those things are the eigenvalues here. So there's a very complex mathematics, and this one I have no time to cover. So anyway, eigenvector is a main thing that giving the data characteristics, but also eigenvalue gives the overall magnitude or measures. So someday that we can have eigen phase is the same as eigen value instead of a vector. Then may be much easier. But to do that, then each value must have a high precision, because we have like all over the world there are the 3 billion or 7 billion people. So we got to have some single number, let's say 71.21174, and we got to have some kind of a precision that will uniquely identify the 7 billion people. So that's not going to be easy. So still it goes by this matrix. So anyway, just remember that using eigenvalue, eigenvector, those things, you can get the features. Remember that what was the feature? Feature was a corner or those points, or it can be an edge or a line, or it can be an area like that. So this the little complex mathematics, but there's measures, the value you can calculate for the features, that one for identifying this, or identifying this line, or identifying this area. And the what you can do is that the overall gradient, what it is that from here the next point is around in here or going this way, and these are the gradients. What direction does it go? So that gradients can be actually calculated with an eigenvalue and eigenvectors. So here those eigenvector can be further that mapped into one eigenvector. So this one is typically the dimensional vector, another one-dimensional vector, but that eventually boil down into single values. So here's a very interesting thing that called the Harris operator. So we have two. This one is a lambda 1, and this direction is a lambda 2. So we have two axes of principal components, and then our function is that the lambda, those products of two the eigenvalues plus sum and over sum of those two values. So this product is known as a determinant of H, Harris's H, and the bottom one, the denominator, is the called the trace, the sum of that, how much they are, and then determinant is how much of a magnitude they are working together. So that is called, actually this one is very good, that how much of a movement before you find a certain end point or the point corner points. So that is called that Harris corner detector or Harris operator. So there's to find those the endpoints like that or like that. There are many techniques, but Harris operator is one very popular. So actually, in that the exercise, the lists, that there is a Harris operator using implemented in the OpenCV, and in Python you can run it. So this is the Harris operator can easily detect the same manner. So using Harris detector, this the horse, the toy horse, is the picture is subject to the operation of the detection. So we process that. Then eventually that goes to the value, the f value, that's a function value. So that's a very high or low. That is part of the calculation. So I'm not going to go to the detail. So, but there are a few places that's a high, that's a low, like that one. So we see that some parts are dark and some parts are the high, the blue. The blue parts, that's a low part, and the red part is high part. So that one will be thresholding and cutting it up like that. Then eventually, you may not see too well, but there are dots. Those things are the detected corner points by that Harris operator. That's a lambda 1 times lambda 2 over lambda 1 plus lambda 2. So those things are showing, but it's very difficult to see. So what you see, I'm sure that you can see that one. Actually, I have exactly same data that I just cut up this data and run through this Harris operator, and it works just fine. So here, that those red dots are where the corners are. That's a red value, that's Harris operator. So we see here that there are a few things like that. And here's a red a corner, and then there's a red corner, that one being showing as kind of a corner points be shown. When this is a little darker, contrast is better, so you see those dots. I actually ran the one picture that I took in at the Mongolia, and you know, that's Terrelgi and those Turtle Rock. And then there's a corner. Those things are got the this detected. This one. Sorry, that this one has different. I'll use different color. So those things are different at the corners. So many corners are detected, and even on here in the GAL side, that those places that there's a by threshold. Some are detected, some are not. So, for example, we could expect that some part of this one be detected as corner, but this is done. Yeah, actually, this is detected, but some of them are not as clearly done. So anyway, this is Harris operator. So invariant is that the more like those kind of value that is not changing. So this one is invariants are very much like the eigen values or vector. That one is very much of a stable. So scale invariant detection, that when we are working on the feature and detect those corner or edges or region, then we want to make sure, we have seen in previous slides that the book can be on the front or they laid down. So those the corner being detected or not detected, to detect it, then we would like to have those some kind of the Harris operator of the definition here. So Harris operators, and then you can detect those corners as a kind of a sudden changes of those tracing order. And this is the range. But idea is that, okay, we want to make sure that this is invariant to the scaling. So sometimes we can see big, or we can see very small. Nevertheless, the whole thing must be consistent. And even if that it is in different shape and different scale of the sizes, we should be able to identify it as the same unit. Then here so what you do is that to find those invariants, that there are got to be long processing. So what it is that you begin with a very small window. Then you make it bigger. So as it gets bigger, bigger, then there's a certain point. So the bigger it is, then this is the precision, the increment in the precision. So we say, oh, even if the scale is big, the difference or the difference in the precision doesn't improve. So it's about this much. So it is a good idea that in statistics and many engineering that you try from small scale to next scale to large scale, next to large, and up to very large scale, and see which one gives you the most economic size. So this is not too big, so you don't have to process this big window, but smaller window, and still gets those efficiency improved as much as this. So this one is called optimal, not maximal, but it's optimal form. So in here, that with this, that you can have the curve can be moved up. So in here, that in this picture, this is the current sizes. But in here, there's a blown up. So this one is the window size wise bigger. So we know that these two have different the optimal location. The best location is shifting big. So we know that this picture is a smaller size than this one. So we can use this one as a clue for what is the scale. So we can make those standardized scale, and then from that scale selection, we make that on as invariant the pattern. And whether it's a big or small, we can just adjust our sizes in the histogram. Then you can easily adjust to your size to the current sizes. So you can rescale it into. So once we do, you have experimented with the different sizes. Then once we have done in the process of finding the uniform sizes, then we have a fixed size of the window for the this pattern to match, whether this is the large portion of a piece or small piece like that. It's a collection of points and the edges and the area or region. And so this one, everything is in standardized sizes. So small, then make it bigger. Large, then shrink it a little smaller, like that one. Then with that, we got a standardized size of a pattern. Then you can easily make a correspondence between this one and that one being, well, right now it's just a circle, so we don't know. But actually, this one is a very large number of pixels. So pixel-wise, that this location group of pixel and this pixel have the same pattern matched. So we can say some of them are points, some of them are edges, some of them are areas, and still you can match those the pattern together. And then so that kind of a technique is also very popular. So just you may not, I didn't cover enough on the detail. So it takes a lot of statistics, but just remember the name SIFT. That is that scale invariant. So we use this word invariant a lot, and then the feature transform. So it is called the SIFT or SIFT, the techniques. So I put this one. You can go to this website and you can find the detailed methodology if you are interested in this one. So you can do the matching pretty much. And SIFT is actually another technique or another example given in the OpenCV. So the mathematics and the logic and the calculation takes so much time maybe, but don't worry, it's all in there in the OpenCV library or function. So all you have to do is call. But they covering this so that you know what you are calling. So that's the idea. And then if you they want to know more about those the eigenfaces like that, this is a very good source. I cannot show you this site, but this is pretty good the source, and there are a lot of examples. So some of you may be interested in doing some projects on face recognition for your senior projects. Then this may be something that you can look in, and there are a lot of sample programs, and just you can just use some of the code and make a very impressive product. The fingerprinting we have been talking about, again, that this is the source that you can jump into, then has a pretty the detailed examples at the end, then all the explanation of the fingerprints that I wrote the similar documents a long time ago, but this one is much the more detailed, so I have to keep in mind. So anyway, we said this one I already showed you at the first day of the class this semester, but most of them are over 65% are loops like that. Then when we look at it, then it's not just kind of a long line of a loop. Then there are some islands, and there's the termination or reach ending, and islands. Some of them is just the dots in there. And the ridge enclosures like that. So some abnormality, that's what it is saying. So from the center, there's loops and a few anomalies, and there are some deltas like that. So those kind of the unique or something unusual shape, that's the feature, of course. So these features are like island, ending, dot, enclosure, bifurcation. Bifurcation is branching out into two. Those kind of and then edge patterns or those curve patterns. Those things are the identifiable feature in the fingerprints. So all there it is that just knowing that what kind of feature you have for a given the fingerprints. So you can use by different filter, but this one is sometimes used for this method for the fingerprint checking by different filters, and you got general patterns. That's different. So what you do is that you have collected the fingerprints, and then you have a filtering. So one direction like that, and sideways this way like that, and so there are four directional the filtering, and then the pattern will show like that. So everybody has a slightly different kind of a pattern showing for those the filters. So using that, you do the match. So you match with the four different units. So but the more frequently used was minutiae based. So those abnormalities are being used. So this is type of minutiae. Minutiae is the minor or very small the unique feature. So like ending, dots, bifurcation, those locations. So from starting point that how much you go and what angle. So from here to this one, then you find one. Then you have from there the next one where you can find this. So you have all those from the center points, that amount of distances that can give you the database for your fingerprints. So every fingerprints can be whatever size, long or short, no problem. That you have a center identified, and from the angle those minutiae are being captured and then compared with the data like this and like this. So those the scale invariance can be easily taken care of by having those radical instead of the radial the angle. So in other words, the distance is that the theta and the r, that kind of a way that you can get this standardized distance away. So we need the invariance of the comparing two images I1 and I2, that's image I, and the transform of the I2 may be transformed. So what kind of transformation we like to do? So again, there may be translation, that's a shifting, and scaling, that's the size of the differences, rotation, share, and the reflection. It can be one of those geometric transformation. So that transformation being applied to, so computer will do a lot of computation over there to get the standard form. So limited 3D rotation as the still part of the shift in scale invariant. So scale-wise, it can generate much of this flexibility, but this rotation-wise, that up to about 60 degrees. So you got a fingerprint in here, and they usually you can put your finger like that or like that, or like that a bit as up to 60 degree left and right may be okay, but you have a upside down, then usually it doesn't work, so you got to do it again, that kind of thing. So usually, because for the save time for the calculation, they are just doing the smaller the numbers of angles. So the invariant, to make an invariant, make sure your detector is invariant, and then design an invariant feature descriptor. So majority of cases it is already taken care of, but in here that when you are designing new system for matching, then you may want to think about the shift this one, or the multiple orientation pictures and the variation. So the Gaussian pyramid can be used for that. So here that the rotation invariant. So we said up to 60 degree is what usually we are working. So this eigenvalues and rotate the patch according to this angle from eigenvalue original set how much they had been switched over, was shifted over. Then you can shift the other picture part with the same angle. And here that the 40 pixel can be reduced to the 40 degree, the 8 pixels, so scale to 1/5 of the sizes, 4 to 8, and then rotate the horizontal and sample this one and get the right match. So we see the triangular part. So say we have a triangle here. So remember that we just make a bigger sample. Usually called mosaic. So when you wanna blur the actual face, then you average out the large patches on the grid. That the same manner that the 40 pixel picture become 8 pixel type of the pattern. So each one you average a 5 by 5 to 1 the average value here, and the 5 by another 5 by 5 of another average value. So you have then 40 pixel originally, that can be reduced to 8 pixels or 8 cells, and you have 8 cells downway. And then this pattern is easier to compare, and also you can calculate this angle and orientation, so you can get your invariant the picture like this, and just switch rotated around to get proper matching up. So in here the you have the mountain original the picture. You have a multiple the scale in here, so you can have a very large one, or even larger one, very large one, and extremely large one. You can make a different one. So multiple scale orientation, that's what MAPS is. So multiple scale and orientation, the larger scale, smaller scale, that'll give you the optimal or most the satisfactory scale that you can work on. So it is more like a pyramid. There's an image pyramid from the like one when you take a picture these days, the camera is so good that is some of them I have seen 6,000 something pixel by the 400 something pixel, but you reduce it into a smaller scale of the up to like 1,000 by 1,000 or the 500 by 500, so you can reduce the sizes or total resolution. Then each time you should do the averaging. Each pixel is averaging of many pixels of previous scale. So that gives the different scale, level of scale of views. It's much like a Google Earth or Google Map that you can have a very high level, like a whole Earth being in one screen. Then you make the deeper, then it gets much more detail. So from whole Earth, then you go to Asian part and Central Asia, Mongolia, and then Ulaanbaatar and a certain location in the map. So that you have been seeing, that's actually this pyramid of the image scaling. So image scale pyramid that can be used for. So scale differences can be taken care of by those invariant patterns being created and standardized sizes. And so scale invariant feature transformation is very much also standardized or the popular techniques. So that's all done by take a 16 by 16. So typically that scale invariant is everything stored in more or less in this size, and the angle is always that edge orientation of gradient minus 90 degree, and weak edges are removed and create histogram of surviving edge orientation. So only this part, this angle. So this angle is most common. Then you will use that kind of a way that you get standardized the features of your unit, whether that's corner, edge, or the area. So that's SIFT or shift. So again, the shift is actually when you go to this website, then you can get a more detailed explanation about those the techniques and the calculation methods. And this is an example that again that you can. There are lots of code available on this site. It's real small, but let's try this one. And then yeah, so I actually went to that the website that's a shift scale invariant feature transformation, and toward the end of it, then there's all nice the code that actually doing shift operation. This one I just added, so it needs some kind of a the matplot and the numpy and the CV2, of course. So this is all available. Of course, you have been using it for your the lab sessions. And then the MSER, that is a maximally stable extremal regions. So what is a maximal? The largest scaled unit of pattern that can be that actually is a feature. That one is not changing or trustworthy. That is the technique given. So this one is distinguishing region by wide baseline stereo. So that's a MSER. Just remember those the name of algorithms. That's all you have to do. You don't have to try to understand all the detail. So in here, maximally the stable one is that here's some kind of the picture. Then you are just reducing it, and which one? You say that the next step. Then at a certain level, there is a level that's maximally the stopping. So in the case, the feature can be matched with those maximally stable image lines. So in other words, that you have certain objects and some portion from the existing data, some portions are not very reliable, but only this part is always reliable. Good example is that when you are using face recognition, that you try to use a forehead and the ear or hair, the features, then may be changing or not so reliable. But your eyes are very stable, nose is very stable, mouth is very stable. So few of those components are very stable and always reliable. So just to use minimum number of those reliable part of those whole pictures for the feature identification or characterizing that specific object, whether that's a face or some the country shape like that. So using that technique is a minimal kind of features that to find the match here. So here the feature distance maybe is F1 in here, and here's F2 here. There's sometimes an error. Same features are used, then we may have this one and this one is different one. This one is the second one. This one is the second from the last one. Still, they are same looking, so they will identify as same objects. But that's okay. So we have then keep doing it. Then we got more and more being identified. And then here's the one picture of some the cathedral, and there's a wall there, and there's some figures on the engraved in the wall, and then you can still, based on certain unique components, you can make a matching, and then you see that how far up they are. So this one, for example, this one and this one is quite different. So the distance is 200. That's way too big, so it's not matching. But this one and this one is 75. This one and this one is 50. That's almost a good match. So usually the match-wise, if it's less than 100, then that can be passing as a match. More than that, then it is not matching, like that. And then you give either it is matched or non-matched. So this one sometimes false, sometimes a positive. So this one is that we have the match. So we decide the decision is a yes, but reality is a no, or it can be yes. And the non-matching and the reality is a no or maybe yes. So that is more like here the true, false, true, false. This is our decision. This is real world truth. So this is okay. You call truth as truth, or you call that's non-matching, that's reality, and you decided as so. That's good. But this one you decide as true, even if it is not matching. This is a false truth. And this one is even if it is true, but you said false. So that's a false, the falsity, like that one. So you can make some kind of mistake. So often called the true positive or true negative, or false positive or false negative, that kind of the decision making problem. So in here, that this is the curve that one gives that the receiver operated characteristics. So how much, the more the false positive rate and the true positive rate. So we want to have as good as to closer to this line, but if not, then how far off is good enough? So you can find the right place that where we can economically accept that this decision is good enough for us. Okay, so in the future, these are the more of recent references, and the more recent the papers about this our argument about this feature detection and matching. So this is not the complete list, you may say, but this is some more additional references you can use. So if you are interested in like writing master's thesis, then this may be the kind of sources you can look for. And there are a lot of applications being used. We already talked about image aligning and three-dimensional construction, tracking, object recognition, and the database and robot navigation. We already said this one as application for feature detection. So the whole point is that we got to find out where is the thing that is interesting to or the important enough to identify. Okay, that's all. So in the object recognition part, that we have this telephone and this shape here. So we have those things as a general silhouette. So eigenvector is in a sense that from actual picture we are getting those general silhouette. Remember those eigenfaces with some ghost-like shapes. So with those general shape, we can match shape. This match for the telephone, old style. Then this shape for the shoes, here. And then this shape for those doll, like that one. And you can do the matching. So based on those features, that is, there's points, corner points, and lines, and then there is the area like that. So that characteristics all combined together and uniquely combined in the either principal component or eigenvalue, eigenvector, and then used for the identification. So object recognition is being done using those kind of the feature detection, and the shift can be used for scale invariant feature transform is the recognizing charging station, communicate with the visual card, teach object recognition, like that. There are many AI related the application for this shift. So shift is very important and very popular these days. So it's well worth that you pay attention to. Again, there are more references and there are more about those the open CV the functions you can use. Okay, that's all for this the part of the lesson. I know this is long. I'm tired, and many of those subjects are little not explained well because it's so much statistics involved, and I just had to jump around. But otherwise, this is the end of 4C PPT. Then we'll start doing more of a segmentation. That's the next subject, and that segmentation PPT is already in the what is HOPE unit. I don't know what is being called HOPE, the utility, or HOPE, the reservoir. So okay, that's all. So this is all, and then one more thing to talk about for this class is that the lab that we did last Wednesday, I started saying that something is wrong on my the handout, but there's nothing wrong on the handout. Everything is correct. So why don't you just up to the part of the this checking whether how the eigenvalue works. So that we have A as a matrix. We are just working 2 by 2 or 3 by 3, and then we have V as a kind of the one-dimensional vector and the lambda. So just making sure that all we got is A. That's the data, but we derive those V. So we multiply A times V. Then that somehow is the same as the lambda times V. So this V, same V is eigenvector, and the specific constant value is eigenvalue. So for second page of the lab, the handout of the left 6 handout, I think, is just verifying it. Just to try that one. Then next time I'll talk about in the lab session how to drive it, and we'll go to something else. Okay, that's all. And thanks for your attention. And this is the end.